chemical energetics. What you have to learn in this is it's related to the energy changes that chemical reactions will cause, right? So we have two types of chemical reactions. We're just going to list some stuff. You have an endothermic reactions, and then exothermic reactions. We'll see what they are in detail later on. There's exothermic and endothermic reactions. Then we'll also learn about their energy profile diagrams or energy pathway diagrams. You have to remember those now, diagrams. And then after that, we'll discuss the different energy changes and their definitions, and their definitions. So this is the most important part of the whole chapter, where you have to learn about different energy changes which are specific to a substance or specific to a typical type of compound. And then whenever it is formed or whenever it is broken down in a certain way, that's basically a specific energy change, and that's how you'll define it. And you should be able to write equations of it for any compound that you're given, right? So different energy changes that you have to learn definitions for, and you should be able to write equations for that also. The fourth topic that you want to do over here is bond energy. Bond energy. We'll learn about what bond energy is. Again, it is an energy change. It is a specific type of energy change, and questions related to bond energy. There's a specific equation that you use for delta H, in which bond energies are used in order to calculate the enthalpy change of a complete reaction. That's what you'll learn over here. So questions are related. And then the fifth part would be of how to experimentally. Before that, we'll do Hess's law. After we've done all the energy changes, we'll learn an energy cycle, which we call Hess's cycle. And what will apply in the Hesse cycle is known as the Hesse's law. Okay, and we'll learn about the law, what the law states, and how do you use it in energy changes. Then you'll learn how to find delta H, or enthalpy change of reaction. There's two specific types of energy changes that you can find out experimentally, but over here I'm just writing delta H of a reaction, which would be neutralization or combustion. These are the two energy changes that you can find experimentally of a reaction experimentally. We'll see how experimentally we can find the energy change delta H of a reaction. And then after that, that's all. There's no more need. So these are the overall basically topics that you need to cover. And this, the most important topics would be from an MCQ point of view. Energy profile diagrams are very important. From an MCQ point of view and theory point of view, this is very important, the definitions and energy changes. Then bond energy and question related, theory related, mostly the questions asked are theory related. Then Hess's law and Hess's cycle, you'll find a fixed question for this in every single past paper from Hess's law or Hess's cycle. And then there's this, which is included in moles whenever they ask a question about enthalpy change, and whenever there is a question about experimentally finding it. Okay, so these are the main topics that we have to cover in this chapter. Anything that might be left out, we'll cover that in the past paper session. And when we do the past papers, anything that is extra and that we find new, we'll automatically add that into our notes later. Clear?
Yep.
So let's start from the first topic, that is of energy changes. That is exothermic and endothermic reactions. Endothermic reactions. So we do know about a reaction. Whenever a reaction occurs, the reactants, for example, you have two reactants, R and A, all right? They will always form products, right?
Yep.
Reactants always convert into products, but how do they convert into products? The reactants break their own bonds. So bond breaking occurs, right? And then when the product is being formed, a new bond is formed, right? So basically A and R break, the atoms break away, and then A and R would join together in order to form product on the right hand side. So bond formation and bond breaking, both processes occur, right? So what happens is that the bond breaking process is endothermic. It requires energy. Whenever you want to break a bond, it requires energy. So you just take a pencil in your hand, you hold them in both hands, the pencils, and then you try to break them. What are you trying to do? Consider that as a bond. What if you want to break the pencil from the middle? What are you going to do? You're going to give it energy, right?
Yep.
So bond breaking requires energy and bond formation is the opposite. It releases energy. So bond breaking is known as endothermic process, not a reaction. It is an endothermic process. Bond breaking, I'll write it as BB. And the bond formation, BF, is exothermic because when bonds are formed, energy is released. All right. So whenever a reaction occurs, both these processes are occurring at the same time. Endothermic process of bond breaking occurs and the exothermic process of bond formation occurs. Now, whether a reaction will be exothermic or endothermic completely depends upon which of these processes had the greater magnitude, which of them happened more, or which had a value, which had a larger value than the other one. So if the bond breaking required more energy than the energy released, which was less energy, then the overall reaction would become what? It would become endothermic because more energy was absorbed in order to break bonds compared to the energy released when new bonds were formed. All right.
So
So what is
endothermic is
dominating the
basically
exothermic process?
when it's basically more energy required to create the bond rather than
Yeah,
released.
we will define that. We will define that. But in this
Okay.
case, the overall effect or overall net reaction would be endothermic. Why? Because the endothermic processes involved more energy compared to the exothermic processes, right? Of bond
Yeah.
formation. The same goes for exothermic reactions. The exothermic reactions would have a magnitude for the energy for bond formation would be greater compared to the energy taken in to break the bonds. So overall net effect of that would be that the whole reaction overall is what is exothermic because more energy was released compared to the energy that was absorbed. Clear?
Yep.
So every single reaction has both these processes, exothermic process and endothermic process. And whichever of these process has a greater magnitude, that is what the reaction then or the nature of the reaction becomes. So the first is exothermic reactions. Now, the easy way to remember exothermic reactions, whether they release energy or gain energy, is to look at exo. Now, from exo, you'll remember exit. All right. And what does thermic mean? It means thermal energy, heat energy. So the heat energy in this reaction exits from the reaction, all right, into the surrounding. So this is our reaction. Reactant goes into product. If the reaction is exothermic, this reaction is known as the system. Okay, this reaction is our system, and whatever is around this reaction is our surrounding. So in exothermic reaction, what is happening? This reaction releases energy, right? Heat energy exits from this reaction. This reaction will also heat energy, but from the system towards the surrounding. It releases energy in the surrounding. How do we know that? If you want to know if a reaction is exothermic or endothermic, what do? You take a beaker, you conduct that reaction, but in the beaker, what do you place? You place a thermometer. If the temperature of the thermometer increases from the initial value, that means that the surrounding, that is water for the reaction, in case of this beaker, there's water around this reaction. So in the surrounding, the temperature is increasing. When will the temperature increase in the surrounding? If it gets some heat energy from somewhere, right? And
Yep.
where is it getting that heat energy from? From this reaction, it's releasing heat energy into the surrounding, due to which the temperature of the surrounding is rising, right? So exothermic reactions, we'll write them as chemical reactions, system to surrounding. So we can write it as release heat energy into the surrounding. This is just for our help. But if you want to write it properly, I'll write on the product side, I'll write plus heat. So they produce a product, but they also release heat. So I'll write that on the product side. Okay? This heat goes into the surrounding, due to which the temperature of the surrounding will start rising. That's how we'll know the reaction that was occurring was exothermic, because the temperature of the surrounding is rising where the thermometer is placed. So in order for that to rise, the reaction must release energy into the surrounding. Clear?
Yeah.
So we define exothermic reactions as chemical reaction in which heat energy is released. Heat energy is released, or you can also say transferred into the surrounding. And when the heat energy travels into the surrounding, what happens? This is an important point. When the heat energy comes into the surrounding, what does the surrounding do? It absorbs that heat energy and increases its temperature, right? So the temperature of the surrounding increases. Okay, let's do an example for this. Let's say that you have magnesium solid and you have H2SO4. This is a metal plus acid reaction. You'll add the magnesium into a solution of H2SO4 and you'll form magnesium sulfate, aqueous, and you'll also get hydrogen gas. And this is a exothermic reaction, so it will also release heat energy. So I'll write plus heat. This heat is released into the surrounding. So it also releases heat energy. Clear? Now, what is our system? This reaction that is occurring is our system. This was our system, the reaction, right? Now, it is releasing energy into the surrounding. So let me just draw a diagram in which we're conducting this experiment. So this is a beaker. In the beaker, we have an H2SO4 solution. We have an H2SO4 solution, which is an aqueous form. And we added magnesium solid into this. And we also placed a thermometer over here. The thermometer has an initial temperature reading. All right. So when you add magnesium, an exothermic reaction takes place. And due to that, the reaction that was occurring, this reaction that is going to occur inside the beaker is going to release heat energy, right? So I'll just write this as a reaction that is occurring, that I just circled. And that reaction is going to release energy. That energy is going to go into the surrounding. What's the surrounding right now?
The outside of the
It's water,
reaction?
right? It's water.
Yeah.
What's the system? System is the reaction that is occurring. That's the system, and it is releasing from system to the surrounding. It's releasing its heat energy. So when this heat comes into the surrounding, what happens to the surrounding? The temperature of the surrounding increases, and we see that on the thermometer. The temperature would increase. Clear? So that's how we'll know that this reaction is exothermic. Are you clear?
Yeah.
Now remember that for exothermic reactions, the symbol or the value of delta H or enthalpy change value is always negative. And we always consider energy changes in which unit, kilojoules per mole is always going to be our unit. That's the standard unit for any energy change. Okay?
Yep.
So delta H is always negative for exothermic. You just need to memorize one of them. The other one is always going to be the opposite. Now let's talk about some examples of exothermic reactions. examples of exothermic reactions. These are the examples that you need to memorize for MCQs. So the first reaction that is exothermic is respiration. Whenever you breathe out on a cold surface, you will see some vapors forming, right?
Yeah.
So that's because it's an exothermic reaction. Heat is released from your mouth, right? That's why the vapors over there are forming. So the first example is respiration. The second example is neutralization reaction. Any neutralization reaction, which is also known as an acid-alkali reaction, is also exothermic, always. All right. And then the third example would be combustion. Whenever you burn coal, what do you feel? Do you feel heat coming towards you?
Yes.
Or do you feel cold when you stand near a burning source?
No, hot.
Yeah, we feel a heating sensation. Why? Because that burning is releasing energy into the surrounding, and that's the heat that is being absorbed by our bodies in order to feel warm, right? So that's combustion. So these three examples would be enough for you to at least know three examples for exothermic reactions, which are the respiration, neutralization, and combustion reactions. All right.
Yeah.
Now let's move on to endothermic reactions. Now, endothermic reaction is the complete opposite. When is a reaction endothermic? When the reactants that needed energy to break the bonds and the products that needed energy to form the bonds. The breaking of bonds is endothermic process and the formation of bonds is exothermic process, right? When is the complete reaction, this overall reaction going to be endothermic? When this energy is greater than the energy that is released when bonds were formed, right? So the overall net change would be that the overall reaction is endothermic, right?
Yeah.
So that's when endothermic reactions are going to happen. So how we define the endothermic reactions is chemical reaction, chemical reaction in which heat energy is absorbed. Heat energy is absorbed by the system. And where does this system take this heat energy from? It takes it from its surroundings. All right. So by the system, from the surroundings. So when you absorb heat from the surrounding, what should happen to the temperature of the surrounding? If you're taking out heat from the surrounding, you're absorbing it, you're using it in the reaction, what should happen to the temperature of the surrounding? Should it increase or decrease?
Decrease.
Yeah. So the temperature of the surrounding decreases. So the surrounding gets colder, right? Or cooler compared to the temperature that it was on before the reaction happened. So temperature of the surrounding decreases. Now we'll take another example. For example, there's a endothermic reaction happening over here. This endothermic reaction means that this endothermic reaction requires energy from the surrounding. This is our surrounding and the reaction is our system. Now, in order for the reaction to proceed, it requires heat energy. So what does it do? It takes the heat energy, the heat in the surrounding and absorbs it. Whatever heat in the surrounding is present, whatever part of that heat it needs, it absorbs that heat energy for the reaction to proceed and make product, right? But where is our thermometer placed? In the surrounding. This is our thermometer where it has an initial temperature like this. I'll write it as T initial. This is our initial temperature. When this heat is getting removed from the surrounding and utilized into the reaction, it goes into the system and this surrounding has the surrounding has lost its heat. What should happen to the surroundings temperature? It should decrease, right? It gets cooler. When this heat is removed from air, the surrounding will start getting cooler due to which the temperature of the surrounding should start dropping instead of rising, right? Again, complete opposite of the whatever was happening in exothermic reaction. Clear?
Yep.
So you'll see a temperature drop in this on the thermometer that is placed into the surrounding. We can only measure the temperature change of the surrounding, not of the system. We can never place a thermometer into a reaction. We can place the thermometer wherever the reaction was occurring or the medium in which the reaction is occurring, right? That's practically possible. But placing a thermometer into the reaction is never possible. Clear?
Yep.
So our temperature starts decreasing. Again, let's go back to, so this endothermic reaction, endo say, you have to remember that endo here stands for enter, or energy is being absorbed. So I'll just write heat energy is absorbed. This is just for our quick learning. So we know that heat energy is absorbed in endothermic because heat is entering into the system. All right. So heat energy is absorbed in this reaction. Clear? Now let's
Yep.
go on to an example. The first example of endothermic reactions would be photosynthesis. Now, during photosynthesis, what do plants do? Apart from all the minerals that they require from the soil, apart from chlorophyll from the sun, what else do they need in order for photosynthesis to proceed?
Light.
Yeah,
So
light.
heat
And
energy.
from that light, they absorb heat energy. Basically, from the sun, they require heat energy in order to conduct photosynthesis. That's why photosynthesis is our first example for endothermic reactions. Apart from this, every kind of decomposition reaction. Decomposition reactions are also endothermic reactions for a substance to decompose, it requires heat energy. All right. So it takes in heat energy, uses that heat energy to decompose itself or break down into simpler substance. Are we clear on this?
Yep.
And again, what should be the sign of delta H for endothermic reactions? So you have an endothermic reaction, the enthalpy change of the reaction, which means the overall net energy change. Since it is an endothermic reaction, the net energy change would always have a positive value. So for exothermic, energy is released, lost to the surrounding. That lost energy is our, it is our loss. So a loss would be negative. And since in endothermic reactions, energy is being utilized, it is being absorbed, it is being useful. That's why it is positive. So it's just a way to remember delta H is positive for endothermic reactions. Clear? And what
Yep.
would be the unit? Since it is an energy change, the unit will always be, the SI unit would always be kilojoules per mole of that substance.
Okay.
Clear?
Yep.
Yeah. So this was about exothermic reactions and endothermic reactions. Now we need to know their energy pathway diagrams or progress of reaction diagrams. You can call them energy profile diagrams. And what do they look like? You've already seen them previously, but let's revise that also. So next would be energy profile diagrams for exo and endo reactions. So how do you draw energy profile diagram? You're just trying to show how the reaction occurs. All right. So on the y-axis in any energy profile diagram, what do you plot on the y-axis? You plot energy on the y-axis, and on the x-axis, you're plotting the path of reaction or the progress of reaction, how the reaction is going to progress, how the reaction is, which path the reaction is going to follow. That's what you're plotting on the x-axis. So what happens is how does the reaction start? Does it start from reactants or products? Where does the reaction start from? It starts from reactants always, right?
Yep.
So you'll make a first flat line that represents your reactants. This is my reactant that is now going to convert into product, right? So for right now, I'm just randomly making the product line over here, but you later on you know why I'm going to make it up or down or higher than the reactant line or lower than the reactant line. Then how do you connect these two? So you have two flat portions. The first flat portion represents the energy of reactant. The second flat portion represents the energy of the product. Now, what happens for the reactant to convert into product? Sometimes the reaction is endothermic. That means the reactant needs to absorb energy in order to form product because endothermic reactions absorb energy. Or sometimes the reaction is exothermic. That means the reactants already have a lot of energy and they want to release that energy in order to make the product, right? So these are the two things that are happening. So how do you join these two lines in an energy profile diagram? You call this you join them like this, and it's known as an energy hump. All right. So I'll call this reactant line. Just the terms. I want you to memorize the terms. We'll call this product line. All right. And then this hump that we made, we'll call it our energy hump. All right. So this is how you draw the progress of a reaction. So what is happening over here? Over here, the reactants need to, because they're on this energy, and in order to make product they need to pass from here first, right? So they need to absorb some energy, right? They need to absorb some energy in order to go into the product, right? So this is just the path that the reactions over here absorb some energy and then they go into the product, right? They convert into the product, but initially they do require some energy to be absorbed in order to make the product. So these are the terms that I want you to memorize. Now let's make an energy profile diagram for first an exothermic reaction and then an endothermic reaction. So I'll write it as EP diagram for endothermic reaction. So endothermic reaction. Now first, before we draw the diagram, remember that whenever an endothermic reaction is occurring, whenever an endothermic reaction is occurring, what is happening? Heat energy is absorbed, right?
Yep.
I want you to memorize it like this. So that means the reactants, they do not have a lot of energy right now in order to convert into product, right? But if they want to convert into product in endothermic reactions, they require energy from outside. They need to absorb energy, right? So the reactant itself had low energy and then it absorbed energy. Since there is an endothermic reaction, it absorbs energy, gets to the level of energy that is required to make the product, and then forms the product. All right. So the
Yep.
reactant itself had less energy, and after it absorbs energy, then it makes the product. What do you think the product's energy would be?
Higher.
Yeah, higher, right? Because those reactants first gained energy and then made a product. So that product now has a lot of energy. So the energy of the products would be greater, right? So this is the first thing that I want you to know for endothermic reactions, that reactants have less energy compared to products because reactants, in order to convert into product, have to absorb energy from outside, then they convert into products, right? This is just a way to memorize this. There are other ways, but I think this would be a bit more easy for you. So let's draw an energy profile diagram for this now. So I'll draw energy on the y-axis. I'll label energy on the y-axis. And then on the x-axis, I'll make the path of reaction. The path of reaction and the progress of reaction. Which line do I draw first? There are two flat lines. The first one is for reactants. The second one should be for products. But now do consider their energies because on the y-axis you have energies, right? So the
Yep.
reactant had less energy compared to the product. So the reactant line should be lower and the product line should be higher in energy. on the y-axis. So when you trace back to the y-axis, the product line is at higher energy and the reactant line is at lower energy. This is the only reason that you're going to do this for, right? How do you connect these two lines? You connect them using a energy hump. So you make an energy hump with which you connect these two. Are we clear?
Yep.
Now I want you to memorize two things, then we'll define them later. All right. So this is the energy profile diagram that you need to draw for exothermic reaction. Sorry, we did endothermic, right? So endothermic reaction. This would be the energy profile diagram. It would look like this. But over here, you have to label two things. What are those two things? We'll come to that in a bit. But before that, we should draw our exothermic reaction energy profile diagram. So if I want to draw it for the EP diagram, energy profile diagram for exothermic reaction, then how should that be? Now I know that in an exothermic reaction, whenever reactants go into product, their energy is released, right? For exothermic reactions, heat energy is released. How is that heat energy released? So for our own help, we'll say that these reactants released energy first into the surrounding, they released energy and then formed a product. So if the reactions were able to release energy, what do you think the energy should be? Higher or lower?
Then it should be lower.
Now, if they were able to release energy, that means they already had a lot of energy. That's why they released their energy into the surrounding, right?
No, I meant like the products should be lower, right? Than
Yeah,
the
but for the
reactants?
reactant, it should be higher. The
Yep.
reactants have a lot of energy. They release some of that energy into the surrounding and then convert into product. When a product is formed from reactants that release their energy, what type of energy should the product over here have?
Lower.
Lower energy. So now we know for exothermic reactions, since reactants release energy, then convert into product, the reactants must have more energy compared to the products, right? Now I can make my energy profile diagram. So energy on the y-axis and the progress or path of reaction on the x-axis. Again, first I'll make the reactant line and then I'll make the product line, then connect them with an energy hump. Who has higher energy in exothermic reactions? A reactant.
Reactants.
So the reactant should be higher, reactant line should be higher, and the product line should be lower. The product line would be lower. Now I need to connect these two. I'll connect them with an energy hump like this. Are we clear till here?
Yeah.
Now there's two things that very important two things that you need to label over here. How do I know this is an energy profile diagram of an exothermic reaction? Or if this is of an endothermic reaction, how do I prove that? So what you need to label over here is enthalpy change of reaction. What is enthalpy change of reaction? It is the net exchange or transfer of energy in the reaction. If that net change is positive, that means it was an endothermic reaction. Because for endothermic reactions, enthalpy change is always positive. If it was an exothermic reaction, the overall energy change would be negative. That means the delta H would be negative, which means it lost energy to the surrounding. So it's an. So now let's move on to the two labelings that you need to be able to do or identify correctly on energy profile diagrams. The first one is known as the activation energy. The activation energy. And how do you define activation energy? The symbol for activation energy is E small a, capital E, and in the subscript you write a small a. Again, unit is also kilojoules per mole. Since it is an energy change or it is energy, the SI unit would be kilojoules per mole. Right? Activation energy is the minimum energy that is required to start a chemical reaction. For instance, if you have petrol And if just leave it on, if it's just, my God, my tongue is twisting right now. So if you have petrol and you just leave it on a surface, would it start burning itself?
I don't think just normally.
It won't start burning itself, right?
Yeah.
It'll just lie over there. But in order to start the burning of that petrol or that any hydrocarbon, what do? You give it an initial spark, right?
Yeah.
And from that point on, it burns itself. What is that initial spark for that petrol? It's its activation energy. That spark provides that minimum energy that was required for the petrol to start burning, right? So activation energy is the same thing. That spark was providing that activation energy to the petrol for it to conduct the combustion of petrol and start burning and keep on burning till it finishes, right? So activation energy is basically that minimum energy that you need to start a chemical reaction. Some chemical reactions start on their own, some do not start on their own, and you have to give them a little bit of energy or a little bit of a push to start them to conduct that reaction. All right? Okay.
Yeah.
So activation energy is basically the minimum energy required to start a chemical reaction. And you can write an example as the energy from a spark for petrol to start burning. That is its activation energy. Clear?
Yeah.
So this is the first thing that you need to be able to label on an energy profile diagram. That's the activation energy. You need to know where the activation energy is going to be labeled on an energy profile diagram. All right. And the second one is the enthalpy change. Enthalpy change. In simple words, it is the overall energy change in a chemical reaction. It is the overall energy change in a chemical reaction. All right. And the symbol for enthalpy change is delta H. And you need to remember that enthalpy changes can be positive or negative. That depends on the nature of the reaction. If the reaction is endothermic, this delta H would always be positive, right? And this delta H would always be negative if the reaction was exothermic. We've learned this previously.
Yeah.
Any confusion over here?
No.
So it is the overall change in a reaction. If that overall change comes out to be negative energy, that means the energy was lost to the surrounding, exothermic reaction. If that overall change becomes positive, that means energy was needed to conduct the reaction, energy was absorbed into the system. So it is an endothermic reaction. Clear? So delta H can be either positive or negative. Again, since it is energy change, that means what? That means the unit would always be kilojoules per mole, even for delta H. So these are the two things that you need to be able to label on an energy profile diagram. All right. And for that, you need to memorize this note. This will help you to find it blindly. You don't need to even think about it. So remember that delta H would always be from reactant line. That's why we learned the names of those lines. Reactant line to product line. Towards product line. That's how you label the delta H of the reaction or enthalpy change of a reaction. All right. And for activation energy, EA, that's always from, again, reactant line to the top of energy hump. Now you do know what energy hump is, right? So we know the term
Yeah.
what we're referring to over here. So whenever you want to label delta H, you want to start from the reactant line, go towards the product line. All right, reactant to product line. And then whenever you want to label the activation energy, then you start from the reactant line and go to the top of the energy hump. And remember, whenever you do this, you'll see that delta H is showing exactly that sign, the positive or negative, which should be required for an endo or exothermic reaction. All right. So let's go back to our energy profile diagrams. We do these diagrams over here. Now, remember that energy values on this y-axis are positive when they go upwards.
Yep.
In this diagram and in this diagram, the energy values are positive while moving up. So in the opposite direction, they would be negative, right? So let's do it for this diagram. This diagram is for endothermic reactions, right? The reactant had less energy. They absorbed a lot of energy and then converted into products. So the product had now larger energy or more energy than the reactants, right? Let's label delta H over here or an enthalpy change. But before labeling that, tell me, what is the enthalpy change sign for endothermic reactions? Should it be positive or negative?
Positive.
It is positive, right? So we'll see that the delta H is going in the positive direction for the energy profile diagram of endothermic reactions. Now let's prove it over here. Now, how do you label delta H? You label it from the reactant line towards the product line. From reactant line towards the product line, this is our delta H. Do you see that this direction is the same direction as the y-axis?
Yeah.
So what should the values of delta H be? Positive or negative?
Positive.
Positive. So since it is an endothermic reaction, do you see that delta H is also positive? So that proves that we made the diagram correctly, right?
Yep.
Second diagram, exothermic. For exothermic reactions, what is the sign for delta H? Delta H must be negative
Negative.
for exothermic
Yeah.
reactions. Now look over here. So how do you label delta H? You start from the reactant line, go towards the product line. So this is our reactant line over here. This is our product line. I'll extend it. And I go from the reactant line towards the product line. This is our delta H. Now look at the direction of the arrow. Is it opposite to the y-axis?
Yeah, it's going opposite.
Yep, it's going opposite. So going up on the y-axis is positive values. Going down on the y-axis would be negative in the opposite direction. So do you see that exothermic reaction, the energy profile diagram is also showing a delta H of negative value,
Yep.
right? So this is how we know that this is an exothermic reaction. So delta H is now labeled correctly. The next thing that we want to label over here is what? The activation energy. Let's label the activation energy over here. So how do you label the activation energy? So we learned a note for that, that activation energy is always from reactant line towards the top of the energy hump, right? So let's go into the endothermic reaction. Now, endothermic reaction, we know that they absorb energy, right? So from the reactant line to the top of energy hump, this is going to be the activation energy for this. We'll label it as EA. Any problem?
No.
From the reactant line to the top of energy hump, that's our activation energy, right? And then for the exothermic reaction, again, start from the reactant line. And where do I go? Do I go towards the product line or towards the top of the energy hump?
The
Yep,
top.
top. So I start from here and I go to the top of the energy hump. So this would be the activation energy for the exothermic reaction.
which
Clear?
is much less. Yep.
Yeah, it is smaller because exothermic reactions, they themselves release energy, but initially they require some energy to start the reaction. Now, coal
Okay.
itself doesn't burn, right?
Yep.
You need to start the burning, and after once this burning has started, it keeps on burning as long as you provide more coal to it. So this is
Okay.
basically the activation energy. So I can say that this was the initial push that was needed for the reactant to start the chemical reaction. After that, it's just a slide down to the particles, sorry, to the product, right? But in endothermic reactions, you need to provide energy. Why? Because the reactants are at very less energy, and in order to convert into product, this much of the energy is required to give them a push, and then finally they slide down to the product. Clear?
Yep.
So this is how you label the energy profile diagrams and draw the energy profile diagrams.